We are now going to look at some very important relative theorems that will be very useful in improving other mathematical truths, both absolute theorems and relative theorems, within our logic. And they're fairly easy to establish, and we'll prove some of them in class, and you'll be asked to try some of the proofs on your own as exercises as well. Okay, so let's look at what each of them says first of all. So the first one says that if we know that both A and B are true, so these are our hypotheses, then we know that A and B is true, right? So if we have A and we have B, then we have A and B. Similarly, if we have as a hypothesis A or A, then certainly we can conclude A, because either A or A must be true. That means that A must be true. Similarly, if we know A is true, then we know that A or any other well-formed formula B is true, because as long as A is true, or is going to be true, this one is going to be particularly helpful because what it says is that we can add any well-formed formula we'd like to any of our hypotheses or absolute theorems by or. So, in particular, if you want to expand the well-formed formula to add other parts, this relative theorem will allow us to do that. And finally, if we have both A and B, then we can conclude A. Similarly, think of this symmetrically. If we have A and B, we could also conclude B. So notice that all of these results are relative theorems. So one important key thing to pay attention to is that we cannot use any of these in equational style proofs because none of these results establish equivalences. So if at any point you want to use any of these results, which will come in very handy, you need to write a Hilbert style proof. Okay, so as I said before, we'll look at the actual proofs of some of these statements in class, and you'll be able to prove some of them on your own. I also mentioned before other examples where a theorem with inside logic can be looked at outside of logic and can help us to establish other metatheorems. So in particular, one important metatheorem is the splitting merging hypotheses, which says the following. So for any formulae A, B, and C, and any set of formulae gamma, we have that any set of hypotheses gamma plus our two well-formed formula A and B, if they prove a well-formed formula C, this is equivalent to, so for example, to prove C, if we need to add both hypotheses A and B to gamma in order to prove C, we could also, or equivalently, add one well-formed formula A and B to gamma to also prove C. So what this is saying, essentially, is that we can either split a hypothesis into two separate hypotheses, or we can merge the hypotheses together into one hypothesis, and doing that, in either of these cases, can prove the same result. This is a direct application of this relative theorem 1 and this relative theorem 4. Okay, so this one is the merging. So if we take two hypotheses, we can merge them together, right? So this is this direction. If we have A and B separately, we can conclude A and B, add that to our hypothesis, and prove C in the same way that we do that here. Or this one here is the splitting hypothesis. So as I had said before, A and B proves A, and A and B proves B. So many times you're going to want to separate hypotheses with an AND into two separate hypotheses to be able to use them to prove some other well-formed formula C. So this, you'll see a number of applications of it, and essentially we're applying either this or this relative theorem. So merging hypotheses together if we need to connect them with an AND, or splitting them apart if we need them separately. Okay, so we'll also look within class at other really important results that you know from 1019, and what we're doing within this particular class is formalizing them. So we're going through this rigorous process to justify why each of these results that you took for granted to be true in Math 1019, so we can actually prove them in this class. So for example, here is modus ponens. which is one that you know very well. Here is something called the cut rule, which we'll apply many, many times in applications in our next section. The transitivity of implications is another result that you know, and also proof by cases. So this is a technique that's used a lot. We in fact used it in our class when we were looking in the semantic portion of section 1.3 when we're proving tautologies and tautological implications. So here is a formalization that this method of proof that many people want to use can be proven outright here. And we'll apply this on occasion as well.